Okay, welcome back. Okay, I want to continue with electrical machines, part 5. I repeat, electrical machines, part 5. Okay, now DOL starters should also incorporate a means of overload protection, which can be operated by either magnetic or thermal overload trips. These activate when there is a sustained increase in current flow. Now, to reverse the motor, you need to interchange any two of the incoming three-phase supply leads. If a further two leads are interchanged, then the motor will rotate in the original direction. Operating principle of a DOL starter. A three-pole switch controls the three-phase supply to the starter. This switch normally includes fuses, which provides a means of electrical isolation and also short circuit protection. We shall look at the operation of the DOL starter in stages. Let us start by looking at the one-way switch again. In this circuit, figure 6.23, the switch is operated by finger and the contacts are then held in place mechanically. We could decide that we do not want to operate the switch this way and instead use a relay. In this system, figure 6.24, when the coil is energized, it creates a magnetic field. Everything in the magnetic field will be pulled in the direction of the arrow and the metal strip will be pulled in onto the contacts. As long as the coil remains energized and is a magnet, the light will stay on. Looking at figures 6.23 and 6.24, we can see that the first option works well enough for its intended purpose. However, it could not be used in a three-phase system as we would need one for each phase and would have to trust to luck each time we tried to hit all three switches at the same time. However, the second option does provide us with an effective method of controlling more than one thing from one switch, as long as they are all in the same magnetic field. Let us apply this knowledge now to a DOL starter. We know that we cannot have three one-way switches in the starter, but it helps to try and think of the contacts where the switches are not operated by finger, but are pulled in the direction of the arrow by the magnetic effect of the coil. 6.25. Items affected by the same magnetic effect are normally shown linked by a dotted line. For ease of explanation, we will use a 240 volt coil. Okay, and here you have your coil, energized coil. Okay, pulling in, creating a magnetic field, pulling these contacts in, which will make a crosshair to your motor. Okay, and therefore that will be the electrical magnetic effect of starting your motor without using your fingers, or I should say losing your fingers. Now figure 6.26 free switch relay with normally open start button, and here you have excuse me. From this we can see that as soon as we put a supply onto the coil, it energizes, becomes a magnet and pulls the contacts in. Obviously this would be no good for our starter, as every time the power is put on the starter will become active and start operating whatever is connected to it. In the case of machinery, this could be very dangerous. The starter design therefore goes one step further to include a no-volt protection. The simple addition of a normally open start button provides this facility as shown in figure 6.26. So far, so good. We now have to make a conscious decision to start the motor. Our next problem thought is that every time we take our finger off the start button, the button springs back out. The supply to the coil is lost and the motor stops. This is the no-volt protection element in operation. I quite like this actually, because here you have, as you take your finger, as you push the button in, the start button in, it starts up the motor. Bring this contactor in and you put a supply to the motor starts. The moment I take my finger off this button drops out, this contactor drops out and the motor stops. I mean, I could be there all day holding this button in forever. So we have to find a way of that. When we press the start button, we have created a condition where the button, once started, goes through a start contact or a retaining coil, which will then hold the start button in place. Well, it would not hold the start button in place, but hold the motor in place through a start contact coil. We'll see as we go on what I'm trying to say, hopefully. So far so good. We now have to make, okay, our next problem thought is that every time we take our finger off the start button, the button springs back out. The supply to the coil is lost and the motor stops. This is no-volt protection element in operation. Okay. What we need for normal operation is a device called the hold-in or retaining contact, as shown in figure 6.27. And here we have our retaining contact. Figure 6.27, we're starting the motor. So we press our button or coil, okay? This holding contact comes in and links out this through the coil, through the stop button, and retain the motor in position, and the motor will continue to start. The moment we press the stop button, that breaks the circuit. That holding contactor drops out and the motor stops. Okay. Well, let's carry on. What we need now for normal operation is a device called a hold-in or retaining contact, as shown in figure 6.27. This is a normally closed contact, position 1, which is also placed in the magnetic field of the coil. Consequently, when the coil is energized, it is also pulled in the direction shown, and in this case across and onto the terminals of the start button, position 2. We can now take our finger off the start button, as the supply will continue to feed the coil by running through the hold-in contact, that is linking out the start button terminals, position 2. This now means that we can only break the coil supply and stop the motor by fitting a stop button. In the case of a starter fitted with a 230 volt coil, this will be a normally closed button placed in the neutral wire. Now, for the fraction of a second that we push the stop button, the supply to the coil is broken, the coil ceases to be a magnet, and the hole in contact returns to its original position, position 1. Since the start button had already returned to its original open position when we released it, when we take our finger off the stop button, everything will be as when we first started. Therefore, any loss of supply will immediately break the supply to the coil and stop the motor. If a supply failure was restored, the equipment could not restart itself. Someone would have to take the conscious decision to do so. This system is basically the same as that of a contactor. In fact, many people refer to this item as the contactor starter. Such starters are also available with 400 volt coil, which is therefore connected across two of the phases. Now remote start stop. Okay, remote start control. Okay, this one is for you to read yourselves. Okay, and look at how this has operates. Okay. In the DOL starter as described, we have the means of stopping and starting the motor from the buttons provided on the starter enclosure. However, there are situations where control of the motor needs to take place from some remote location. This could be, for example, in a college workshop where, in the case of an emergency stop buttons located throughout the workshop can be activated to break the supply to a motor. Equally, because of the immediate environment around the motor, it may be necessary to operate it from a different location. Commonly known as a remote stop-start station, the enclosure usually houses a start and a stop button connected in series. However, depending on the circumstances, it is also possible to have an additional button included to give inch control of a motor. If we use the example for the oil starter as described in the previous diagrams, but now include the remote stop-start station, the circuit would look as in figure 6.28. Below, where for ease the additional circuitry has been shown in red. Okay. As can be seen, the remote start button is effectively in parallel with the start button on the main enclosure, with the supply to both of these buttons being routed via the stop button of the remote station. If the intention is to provide only emergency stops, omit the remote station shown so that these are all connected in series with the stop button on the main enclosure. Hand operated star delta starter. Well, this is a grand start. Let me just see if I can make this a little bit bigger for you to look at. Hand operated delta starter, okay. And let me go down, I'm going to bring this across. Okay. Now the connections of the motor must be arranged for star delta starting with both ends of each phase and winding 6 in all brought out through the motor terminal box. The starter itself in its simplest form is in effect a changeover switch, figure 6.29, gives the elementary connection to both star and delta. Okay. 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 Oh, yeah. When the motor windings are connected in star, the voltage applied to each phase winding is reduced to 58% of the line voltage. Thus, the current in the winding is correspondingly reduced to 50% of the normal starting value. Applying these reduced values to the typical three-phase squirrel cage induction motor, we would have initial starting current of about 2 to 3.5 times full load current and initial starting torque of about 50% full load value. The changeover from star to delta should be made when the motor has reached a steady speed on star connection, at which point the windings will now receive full line voltage and draw full weighted current. If the operator does not move the handle quickly from the start to run position, the motor may be disconnected from the supply long enough for the motor speed to fall considerably. When the handle is eventually put into the run position, the motor will therefore take a large current before accelerating up to speed again. This surge current could be large enough to cause a noticeable voltage dip. To prevent this, a mechanical interlock is fitted to the operating handle. However, in reality, the handle must be moved quickly from start to run position, otherwise the interlock jams the handle in the start position. The advantage of this type of starter is that it is relatively cheap. It is best suited for motors against no load or high loads, and it also incorporates no volt protection and overload protection. And here we have a picture of a Star Delta starter, okay. Let me just drop this down one. Okay. Automatic Star Delta starter, okay. Let me just make sure I can come back and bring your interview into full view. Okay. Now this one I'm going to leave to you to sort out, to read for yourselves, okay? Automatic Star Delta starter. Now soft starters. The soft starter is a type of reduced voltage starter that reduces the starting torque for AC induction motors. The soft starter is in series with the supply to the motor and uses solid state devices to control the current flow and therefore the voltage applied to the motor. In theory, soft starters can be connected in series with the line voltage applied to the motor or can be connected inside the delta loop of a delta connected motor, thereby controlling the voltage applied to each winding. Soft starters can also have a soft stop function, which is the exact opposite to soft start. This sees the voltage gradually reduce and thus a reduction in the torque capacity of the motor. Okay. Okay, I hope you found this useful. Let me just make my way back up slowly. Okay. Nothing for me to say here. I'm just recapping, making sure that we got everything in frame. Okay, that's all I'm making sure I'm doing. Okay, so just bear with me. Okay. Okay, thank you. Okay, thank you. I hope you found this useful. Have a good day. Bye bye.